equals to 0, this is equals to 0. Similarly, for 2D or 3D, we can show that the equilibrium equation can be given as del dot sigma plus V is equals to 0. This is stress tensor and this is force per unit volume, which is also known as body force. So this is stress method of weighted. In the method of weighted residuals, first one with what is collocation. Second one is least square minimization. And today what we'll discuss is Galerkin method. And next one is method of moments. So before I proceed further, I just want to tell you something, that method of weighted residual defines, last time what we have taken is d square u by dx square plus u is equals to 0 and ae we consider it as 1. So I can make this one as simply 1. So then this will become something like this, with a boundary condition such that u of 0 is equals to 0, u dash 1 is equals to 1. That is, last is a bar whose a times e or e times a is equals to 1, and the load thing is also equals to 1 with a uniformly distributed load all along the length proportional to u itself. So when I just write here u, you need to understand that u means u is a function of x. Further, we define that u is our exact solution and u tilde is my approximation. That means I have an error. So therefore, if I substitute instead of u in this, I substitute u tilde, I will end up with a residue which is a function of x is defined as d square u tilde of dx2 plus u tilde, and these thing need not be equals to 0. So this as the starting point, the method of weighted residual says that the integral of this residue integrated over some domain with some weighing function w of x is equals to 0. So in our case, our omega is from 0, 0 to 1. Okay, and for point collocation, W of x is nothing but a delta function of x minus xi. So in the last example in the lecture 4, what we have seen is we have taken W at 0.4. That is also nothing but we have taken our weight to be x minus 0.5 is equals to 0. And with that, we derived the things for the first something. We assumed our u tilde to be a naught plus a1 x plus a2 x square. Since we have shown that, let me open it up. This is what we have shown in the previous class, and we showed that our u tilde after substitution of the boundary condition turns out to be -1, sorry, is given as x minus x square by 2 plus x square by 2 is u tilde after satisfying the essential boundary conditions. So essential boundary conditions are nothing but your displacement boundary conditions. Now similarly what we have done, we took this u and then substitute in our residue using this, and then we found out by enforcing the residue at r of 0.5 equals to 0, and then we estimated our a1, and once you got this a1 you substituted back in this to define your things. Similarly in the b, which is nothing but least square minimization, what we have done is in the least square minimization it is integral of 0 to 1 to w by sorry so then nothing but our w is defined as 2r by 2a1. You can always write it as 2w1. This is our definition of weight, and then based on this integral we determine what is our a1. Once that is done, then we put back our a in the above expression. Similarly, now we will study something called as Galerkin method. Before writing the Galerkin method, I would rewrite my u tilde in a special form. So I want to write my u tilde as where a naught, a1, a2 are coefficients. Let me see, I'm getting some messages. Uh, that is u of or u tilde of 0 is equals to 0. That implies a naught. Let us choose p1, p2, p3. Here I choose my basis function p naught as 1, p1 as x, and p2 as x square. Here I'm just using simple polynomial things which are 1x x square. Some people can at a later point you can see that the any legendary or any kind of a polynomial basis can be chosen. I am using a simple kind of method of movement kind of a thing because it is simple to understand. The problem with these kind of things are they are not orthonormal in nature. But if you take legendary polynomials, phi naught as a function of some polynomial, phi naught, legendary polynomials, they are orthonormal to each other. So anyway, let's keep this simple. So then it is 1 phi1. When I substitute at 0, it is sorry a1 into 1 sorry 0 plus a2 to 0 square. That implies my a naught is equals to 0. Similarly, u dash of x is equals to a1 plus 2a2 x. But we know that u dash of 1 is equals to 1 implies a1 plus 2a2 into 1. That implies a2, or you can write whichever you want to write it as. Let's write it a2 in terms of a1. a2 is equals to 1 minus 2. So once this is very similar to what we have done previously. However, you see that u tilde of x will now become a1 x minus x square by 2. It is same as what we have done previously. So I'm just copying for the lack of time. Plus x square by 2. So this is nothing but we can write it in this terms. However, in the Galerkin method, we choose our weight in the Galerkin function is defined as So that means my way will become automatically v1 minus v2 by 2 in this case, which is nothing but x minus x square by 2. With this as my weight, now I'm in my method of weighted residual, which is nothing but so I will integrate it using x minus x square by 2 plus into the residue is d square u tilde by dx square plus u tilde. So that means I will take 0 to 1 x minus x square by 2 and I can write this one as 2a2 plus a1. Sorry, we should have done it in the other way around. If this is u tilde, this is u tilde. Anyway, that will also have given me the same thing. Du tilde 1 minus x plus x du tilde dx2 will be minus a1 plus 1, which is nothing but so I'm using this expression d square u tilde by dx2 that has to be equated to 0. So one we can again multiply it. So anyway, I will not do this calculation. I will leave it as homework for you. You try it out because it's a simple integration that will kill our time. So only thing here we need to understand that for the Galerkin method, w of x I is defined as dou u tilde by dou ai. That is our definition of weight in terms of Galerkin method. This is for the Galerkin method. I would ask you guys to do this integration and determine what is A1 and report me in the next class. So I don't want to just keep doing a simple stuff because we are running short of time because of lack of um, because of connectivity problems. We have lost our time. So this is a simple integration. I would suggest you do it. So this is what is the thing that you just do it in the Galerkin method. One has to note down at this point is Galerkin method is the modern method. From the Galerkin itself, the actual from the traditional finite element, the modern finite element has evolved from the Galerkin methods. Okay, you will see that this thing will automatically will determine some kind of a psi function, which is nothing but your shape functions will also be determined through the same thing psi I. So the modern finite element has its roots, heavy roots in the Galerkin method. So anyway, with this we will end the Galerkin method, and then the last method I would suggest. Now let us say that we are at point A. Let me see, I might have got few messages. We need to go to the point B. Let's say this is city and this is airport. And for example, you want to catch a flight, and what is your aim? You want to reach from point A to point B in shortest time. Okay, that is your principle. Let's say if you are a cab driver, it would not be your thing. For a cab driver, his aim would be something like, what is the but minimum number of kilometers or economical drive. So each one has a different criteria. But let us suppose that the criteria in our case is not any money saving. It is about reaching this thing as fast as possible. So then you can say that this is one possible path in which you can reach from point A to point B. But not always the shortest distance path is energetically efficient. So if you're taking a small gullies or small kind of lanes, you'll end up going to the airport in this manner, or you can end up into some kind of a weird format and then reach here, or you can go in something like any different path and reach here. Okay, but you need to understand that first one, the observations. Starting point, let's say this is route, this is route 1, this is route 2, this is route 3, and this is route 4. In all the things, starting point is A for all routes. Next, ending point is B for all the routes. Suppose, let me pick something else. This, let me call it as fifth one. For the fifth one, it is not a solution because you are not starting from your place, you are starting from somewhere else, and you are ending at somewhere else. So the 5 is not a valid solution, but 1, 2, 3, 4 routes are valid solutions. Okay, so out of this valid solution, the one which is best suits you has to be determined. The same thing applies in the finite element methods. So let us see what is that. In order to do that, first let me give you a simple example of energy minimization. So first let's start with an energy concept, because energy is required to write a potential form. So for that, let me take an example of spring is pulled with a force P whose stiffness is K. So now let's write its strain energy. Strain energy U is equals to How is the strain energy? Let's draw the curve. So when it is, there is no force, there is, sorry, when there is no force, there is no displacement. Okay, and as the force increases or as the displacement increases, so this is our displacement x. The force versus displacement curve is a linear curve. Okay, the slope of this is k. So the area under this will give you the strain energy. So this value is k times x for a given value of x displacement. So the area of the triangle is 1 times force into displacement, that is equals to 1/2 k x times x, that is equals to 1/2 kx square is your strain energy. Now you can write the external force has done a work on the system, so that is nothing but p times x. Since it is work done, it is minus. So your total potential energy is nothing but u plus v, that is equals to 1/2 k into x square minus px. So this is our total potential energy. The system has this amount of potential energy. Now, what is equilibrium? The equilibrium is a state in which the potential energy reaches a minimum value or a stationary value. For that, I want to explain through some basic single variable calculus. Now, let this is aside. Let us take some surface. Now, if I try to keep a ball here, ball B, or a ball B here, or a ball here, which is the stationary one? The one on the top may be stationary, the one on the bottom on the thing may be stationary. So this position 1, this position 2, and this position 3. So position 1 is meta-stable. That means a small force, a small disturbance will make this ball to come to position 3. Now further, the position 3 is stable because it is under valley. So that means, let me write a function is this is a f of x. The locus of this curve is defined as f of x, or if I want to write in its neighborhood, so I can write it as f of x plus f dash x into h by 1 factorial plus f double dash x into h square by 2 factorial plus order of h cube. So that means, how will you say that position 1 and position 3 are stable? So for position 1 and 3, your f dash x is equals to 0. That means if I take the slope of this curve at this point, the slope, it is the tangent at this place is straight. Similarly, the tangent at that means f dash x is equals to 0 for both the things. So for maxima or a minima or for a metastable and a stable configuration, your first derivative is 0. For both the things, your first derivative is 0. Now, how can you say that it is stable or unstable? Actually, this is sufficient, but I'm just telling you about the second derivative also. So let's also see the second derivative. So f double dash x. Now we have seen that, let's say we are at this position. Now if I want to measure at a small neighborhood h, either this side or that side from this point position, its value is less than the position at 1. So anyway, the second term goes to 0 because the f dash x is equals to 0 and h square is always positive. So f of x plus h can be smaller than this summation only when the second derivative is less than 0. So if it is less than 0, it is maxima or position 1, that is metastable position. Now similarly, f double dash x has to be greater than 0. For let's say you are here, and even if you go this side or you go to the other side, the value of f is always increasing. So it should be more than, this value should be more than this. That can only happen anyway the second term is 0. If f double dash is positive, anyway h square is positive. So it is for minima. Anyway, this is not our maxima, minima is not our criteria, but any maxima and minima you need to see that this is a condition of being stationary. Stationary means either it reaches maxima or minima when its first derivative is equals to 0. So, but you need to understand that this what example I have shown is for a single variable calculus. Now, when variation calculus is introduced, it is not for a single variable calculus, but it is I is nothing but a function of, to know how this as being, will come to the main concept. Now your I is not a function, it is called functional. Functional is function of functions, right? So this is what we need to do. That means at this case anyway, I will show that we have only one function. I is a function of x, which is defined as half of ax square minus bx. So for the minimization, delta I has to be equal to 0. So delta I can be written as di by dx delta x. So that means for the minimization, this first derivative has to be equals to 0. So then I will take di by dx, that is equals to a into x, because this half and that half gets cancelled, and minus p is equals to 0. This is also known as stationary condition. So either it is a maxima or minima, we don't care about it, is it a maxima or minima, we only seek for a minimization. So here also if you see that it is same as this condition f dash equals to 0. So what I'm taking is I'm taking I with respect to a function. X is a function, X is not a variable here, X is considered as a function. So this is nothing but stationary condition will give rise to equilibrium. The stationary conditions will give rise to equilibrium. That means my force is equals to K times X, which is very simple. For single degree of freedom, you don't have to do all these things. If you go back, you can say that the internal resistance is K into X, the internal force is Kx, which is resistance of the system, to the externally applied force P. So if you seek for force equilibrium, P is equals to Kx, that is what you can write it easily. But for a multi-degree or a continuous system, writing the equilibrium equation or force balancing equation, the conservation of linear momentum is not that easier. It is better to come through these kind of minimization. So these energy concept will be quite useful for you at the later point of time. So with this as a background for the 1D example, I will go further and teach you some more variational principles. So let's get back to the variational principles. So for suppose, let's take I as our kind of potential or objective function, which is defined as A to B and integration of some x u u dash u double dash so on dx. So for example, if I take a bar example, x is my position, u is my displacement, and u dash is du by dx, the gradient of it. And similarly for a beam, let's say this, the one we are measuring in the thing is w, so x is again measured in this direction, so w is transverse displacement, w dash is slope, measure of slope, w double dash is curvature, etc. So it depends upon similar, that means it is x w w dash double w double dash, etc. So if I is a functional which is function of function integrated in this manner, then we want a condition where this can be minimized. We need a stationary condition based on that. So anyway, let here we define u dash is du by dx. Now let us take u tilde, which is an approximation. U tilde is nothing but your exact solution plus delta u. Now, okay, let me see, I'm getting a few messages. No? Okay. Now, at this point of time, I just want to explain what I am writing. So let me see, this is point A and this is point B. Let's say from here to here, the exact solution is, this is, the exact solution is u. Now to the exact solution, I'm corrupting my exact solution, so I'm introducing some perturbation. If I perturb the system, the error or the approximation will have exact solution plus a deviation. So you can consider this as a deviation. So your approximate solution is nothing but your exact solution plus a deviation. For example, u tilde is this plus certain deviation. So this deviation is delta u. So how many deviations can be there? There can be n number of deviations. The approximate solution is nothing but exact solution plus deviation. Now you see that u tilde can only be an approximate solution if there is no deviation at point A and point B, because they have to start from the same starting point and end at the same. Anywhere in between you can have a deviation, but not at point A and not at point B. Otherwise it is not the solution of your problem. Let's say a cab starts from not your home, from your friend's home, and doesn't take to the airport but goes to a railway station. Is this a valid route for your journey? No. So it has to start from your home and should end at the airport. So then only it is a valid solution you can take. That's a solution, but is it a good solution? We never know. So that's what we are going to construct in this given point of time. So now what I do is I'll try to seek the variation of, this is because of a function f variation or approximation. Sorry, function u. This is regarding the function u, all possible choices. Now I want to write for the function f, which is a function of several other functions. So let me write my delta f, or I can write my f tilde as f plus variation. This is not du. Delta f is not same as df. For single variable, this is the change in the function. But delta f is not the change in function, but it is the deviation of the function, which comes from, so only delta f is a small increment, but df is a small increment, delta f is variation. So this is called variation. This is increment. So don't confuse between the df and delta f, they both are different. So anyway, delta f can be written as dou f by dou u and the variation in u plus dou f by dou u dash delta u dash and so on. Let's assume that our function f is only function of x, u and u dash alone. So in that case, this is your variation in the f. Now my delta I is nothing but, or I can write it as I tilde is nothing but I plus delta I. So my delta I is nothing but integral a to b delta f. The variation in the integral of the variation in the delta f will give you, write it again as a to b and sorry, delta f dx. So dou f by dou u delta u plus dou f by dou u dash delta u dash dx is my variation. Now we know that for stationary condition, of I, delta I has to be equals to 0. Now that means this implies this value equals to 0. Now this is on the I, but we want the condition on in terms of F. To do that, what I will do is I will introduce something which you all might have seen. Integration by parts. If you don't know integration by parts, it is very simple. So anyway, you know integration or differentiation by parts, right? Or UV rule. So let's say d by dx of uv is equals to, if I integrate it with respect to dx, I can simply write it as a to b minus, sorry, equals to integral of u dv by dx a to b plus integral v du dx a to b, or I can simplify it further and I can write it as integral v u dash, and this is v dash dx is equals to uv a to b minus of v v dash u dx a to b. Now at this point of time, I know there are so many equations you started hitting it, so I just want to give a very light comment. You might be liking it or not, but anyway, we all used to celebrate birthdays. I think you also celebrate birthdays in your college, right, as a students. So we also as a student used to celebrate birthdays very good, in very, I mean, what do you call, as a big celebrations. So especially on the night, the birthday boy or a girl, I don't know, but the girl get um, bumps depending upon their age. So however, in our college there was one rule which you can apply. You can transfer half of the beatings to one of your friend, and the the guy has to be your best friend, not your enemy. So the same thing here. So if you see that, if you have a differential criteria on u dash, you can give your beatings to your friend v, provided he is a best friend. So this is what even finite element uses it. So this integration by parts, I will use it in the above formulation, and then I will try to use again like delta I is equals to integral a to b dou f by dou u delta u delta x dx plus integral dou f dou u dash delta u dash dx. Now let's consider this fellow as v and this as u dash in the previous case. That can be changed into these things. So it is equal. So then I can write the first term remains same as it is, but the next one will become integral of d by dx of dou f by dou u dash delta u dx a to b plus dou f by dou u dash delta u a to b equals a to b. Anyway, we know that this has to be equals to 0. So this has to be equal. Now you see the measure in this first part and the other part is 0. So I can rewrite it as in a dou f by dou u minus d by dx of dou f by dou u dash delta u dx plus dou f by dou u dash delta u a to b equals to 0. Now let us see one small thing. So in this I've told you that delta u is equals to 0 at a and b. If it is not, you can never, no matter which route you choose, that route has to start at your home only and it should end at the airport only. So the deviation of the path at the starting and the ending is 0. But anywhere in between, delta u of x is not necessarily equals to 0, anywhere in between. So that means you can easily see that these are like your 0 component. Now delta u is any variation in the path. For any given variation, now your delta I has to be 0, means your integrand has to be 0. So that means dou f by dou u minus d by dx of dou f by dou u dash has to be equals to 0. And this is the condition of stationary for the I, which is defined as integral of a to b f of x comma u dash dx. For this to be getting a stationary value, the function should satisfy this set of equation, and this set of equation is also known as Euler-Lagrange condition or EL conditions. So any function f which satisfies any functional f which satisfies this give you the condition of equilibrium for a given case. For example, consider a case of a bar. Consider a case of a bar. You can write I as a function of u can be easily written as the total potential energy available 0 to L 1/2 B du by dx whole square minus q of this is the internal energy, this is the external work done for a bar, and then you can show that if I want to do a minimized equation, what you need to do is you take this function f, which is nothing but f. You can see that f can be function of x, u and u dash. However, in this case, it is only function of u dash. You can as well as 0 to L b u dash whole square by 2 dx. So that means you can clearly show that, and you can even write if you have this one also into the picture, you can easily write this together. They are function of both x and u dash using the thing. So you can introduce a delta function and then you can write it in the form. So the method of at this point of time, I will what we'll do is we'll try to seek delta I. So let me just compare the things. So delta I q dw. So yeah, this is, so we need to seek this equation. What we need to satisfy is we need to satisfy dou f by dou u minus d by dx of equals to 0. So anyways, this I need to just do something, I have missed it. So what we'll do, we'll continue this in the next class. Let me stop at this point since it's already close to 4 o'clock. I'll try to continue the next class, but your Euler-Lagrange condition is given by this one. From this is what is the Euler-Lagrange equation. And this is required for to get the stationary value, and the stationary value will give you your equilibrium condition on minimizing it. That means delta I is equals to 0. Condition is same as this, which is nothing but stationary value or gives you equilibrium condition. So at this point of time, we will take a break and we'll continue on the Friday's class, where I will show this example, finish the example, and then I'll continue with one, pick up the unit 2. So let me take few questions at this point of time and then we'll end the class.